Hello, Algebra 1 students. Welcome to lesson 6.4. 6.4 and 6.5 actually cover pretty much the same material. 6.5 just steps up the difficulty level a bit, and 6.4 is more of an introduction. At least half of the time you've allotted to this lesson is going to be spent practicing problems. The first page and a half or so is learning the steps, and then the second half is practicing. So, without further ado, let's get to it. For pretty much any new type of equation, we want you, the students, to be able to do two specific things. If we give you an equation, in this case we're dealing with exponential equations, we need you to be able to isolate x, or at least determine what the value of x is that makes the left side equal to the right. Second, we need you to be able to graph an equation, in this case an exponential equation. We're not going to do graphing until the second half of this unit, but today and tomorrow are really on solving exponential equations using algebra. It's going to take everything we've learned over the last 3 days to understand our answers. So let's get to it. There's an opener here, and your job is to maybe not necessarily solve each equation, but find the value of x that makes the left side equal to the right. Alright, so if you're looking at that first problem, 2x equals 6. Well, we learned last semester a way to isolate x, but don't let a method or a formula overwhelm you or let you forget how or why the equation is set up the way it is. This says 2 times x equals 6. Well, you know 2 times what equals 6? Tell me, 2 times what equals 6? That's right, 2 times 3 equals 6, so x is 3, right? And we know that because, BEC for because, 2 times 3 equals 6. Cool, we're done. Now, if you wanted to use the method we learned last semester, and that's not a bad thing, we learned SADMAP, backwards Pemdas. And so we look for the number that's attached to x, in this case it's a 2, and it's attached by multiplication. Next to multiplication is division, so that tells us to undo multiplication. We divide both sides by 2, and we find x equals 3. And that's a very valid method for solving. Until we get to problem 2. Problem 2 says 4 to what power is 16? And so if we wanted to use SADMAP, the first thing we have to ask ourselves is, how is the x attached to the 4? Well, don't say multiplication. If the x was attached by multiplication, it would be 4 times x equals 16. This x is not a large number. It's not a base. It's up here. That x is an exponent. And so we'd do the same process, but we'd go down to the e here and say, okay, to undo exponents we use, oh wait, there's no letter next to the e. Huh. Well, SADMAP doesn't really work for us in this case. We don't actually know how to undo exponents. In fact, fun fact, we're not going to learn how to undo x as an exponent until 2 years down the road, or until you take Algebra 2. So I guess we're going to have to fall back on the first method of what is the value that makes sense. And we filled out in 6.3 a table of perfect squares and perfect cubes. You're probably going to want that table of perfect squares and perfect cubes for you today. Because you're going to check and you're going to say, oh, 4 to what power is 16? I think 2 is the right answer here. And that's because 4 to the second power is 4 times 4, which is 16. All right, well, let's move on to the third one. 3 to what power is 1? Ooh, do you remember this? You might be tempted to say 3 to the first power is 1, but 3 to the first power means 1, 3. And so 3 to the first power is just 3. However, there's a very special number in exponentials, and that is 0. We need to remember that 3 to the 0th power, anything to the 0th power, is always 1. And if you want an explanation on why, you can go back and watch lesson 6.2 when we learned negative exponents. So our answer here is x equals 0. Our fourth problem is a little bit interesting. Our fourth problem is going to bring up a few questions here. Well, the first question that my students always ask, and I think it's a brilliant question, is, are we allowed to do 2 times, this is attached by multiplication, 2 times 5? Well, let's try it. 2 times 5 is certainly 10. Okay, and that equals 50. Well, I'm a little bit confused here because I know a few powers of 10. 10 to the 0th is 1, 10 to the 1st is 10, and 10 squared is 100. And we jumped from 10 all the way up to 50. We didn't get a nice answer here. So it is possible this isn't a nice answer. But what if we applied a little bit of algebra here? What if we looked at this problem again? 2 times 5 to the x equals 50. We know that we're allowed to undo the 2 that's multiplying any time. That's just attached by multiplication. Let's do that to both sides. This gives us 5 to the x equals 25. And I bet you probably know this answer. 5 to what power is 25? Well, hopefully you said 2. 5 to the second is 25. 5 to the second, 5 times 5 is 25. Excellent. So the right answer is 2. But 2 doesn't work over here. 10 squared is not 50. 10 squared is 100. And so it's important for you to realize that we cannot multiply by 2. The reason why is because we're really trying to follow Pemdas if you multiply. And Pemdas says you have to take care of the exponent first. Because we can't do 5 to the power, it blocks the 2 from multiplying in. So this is not allowed. All right, 2 to go. Let's see here. I see a few numbers attached to 2 to the x. It looks like there's a 3 that's multiplying and a 1 that is subtracting. Well, let's undo, and let's follow SADMAP, right? Let's undo addition and subtraction first, and we'll do that by adding 1 to each side. This gives us 3 times 2 to the x. Let's see, 23 plus 1, that's 24. Then we can divide off the 3 that's out front. And that leaves us with 2 to the x equals 8. Pretty much every exponent, one or two exceptions, but pretty much every exponent for today is going to be found in your perfect squares or cubes table. So we should probably look for 8 and think, how many 2's does it take to make 8? Well, I think x has to be 3, because 2 to the third, which is 2 times 2, that's 4, times a third 2, that is 8. All right, last one. 4 to the x equals 10. Let's do what we did with the 10s up above. We know 4 to the 0th is 1. 1 is too small. 4 to the first is 4. 4 is too small. 4 squared is 16. 16 is too large. 10 is somewhere in between 4 and 16, which means x is somewhere in between 1 and 2. So hopefully you have your calculator handy. Let's see how close you can get. Take out that calculator, and we know x is going to be 1 point something, in between 1 and 2. So go ahead and try on your calculator 4 to the power of 1 point something. And remember, we learned with our blue calculators, you do 4 to the power of 1 point something. And let's see how close you can get to an answer of 10. Well, how close did you get? Many of my students were able to come up with x equal to about 1.6, and they were pretty good. If you were really good, you'd find that isn't exactly 10. You could get 1.66. In fact, you could go further, 1.6609640474, and that would be really, really close to 10, but it's still not 10. In fact, in order to get a perfect answer up here, to get exactly 10, you would need to write out an infinite number of numbers past the decimal. And unfortunately, there is no way to write this as a fraction to make it much more easier to plug in. You have to write every number past the decimal. And that would be obnoxious. So good news for you. This year, not until Algebra 2, this year we're not going to find any of those answers that are these non-nice decimals. We call these irrational numbers. So let's do a quick conclusion, then talk about what we're learning today. This semester we are only solving exponential equations. And those are equations that have x. Take a look at all of these x's up here. These are equations that have x as an exponent. And our exponential equations are only going to have nice rational answers. Nothing like this. This is irrational. It is solvable in Algebra 2, but not now. All of our answers are going to be either fractions like 1/2 or nice whole numbers like 1 or 2, or maybe some negatives like -1 or -1/2. As we mentioned, problem 6 had an irrational answer. That's an answer that cannot be written as a fraction. And you know another very popular number that can't be written as a fraction? That's pi. All right, to solve exponential equations algebraically, to get these nice rational answers, we actually only have 2 steps, and only one of the 2 steps is somewhat new. This can get a little tricky though, so pay close attention, and we're going to get a lot of practice in today to make sure you're comfortable with it. So, our very first step is to realize that we want eventually to make the left side of the problem equal to the right. And these exponential equations have 2 parts to them. They're always going to have a base on each side, and our bases are, of course, the big numbers. We're going to start by working with those bases first, and we're going to try to make sure that those bases are equal. And in fact, we're not even going to solve the rest of these for now. On these first 6 questions, we are just going to rewrite them so that all the bases are equal. We're going to not even worry about the exponents, and I'll show you what I mean. So, problem 1. We have 3 to the x equals 9 up here. Well, currently, the base is 3 and the base is 9, and those are not the same base. Clearly, 3 is not the same as 9. So we are going to change one, or sometimes both, of those bases to be the same number. And in my last 12 or so years of experience, I found that it's easier to change the larger number into the smaller one. So I'm going to take the 9 and I'm going to rewrite it as 3. Well, am I done? Hopefully you're shaking your head in a bit of confusion, because we can't just randomly change 9 to 3. That would be silly. 9 and 3 aren't the same number. But we can change 9 into 3 to some power. 3 to what power is 9? Think squares and cubes. Hopefully you said 3 squared is 9. 3 times 3 is 9, right? And so all I really did here is I wrote 9 in a different way. And now, look, the bases, the big numbers, are equal. And that is all we're doing on this front page. We're not even going to worry about the fact that this exponent's an x and this is a 2. We don't care about those. We are just making the bases equal. Now you might ask the perfectly valid question, how come we're doing this? I already know the answer. 3 to the x equals 9. X has to be 2. 3 squared is 9. I'm done. Why are we doing this extra step? Well, we're doing that extra step so that when we get to harder or trickier problems, we are very comfortable making the bases the same, because as we'll find, making the bases equal makes the problem much, much easier to solve, no matter how complicated it may look. So we have 5 more of these, and some of them are a little trickier than others. So I'd like you to go ahead and try, and then if you get stuck, unpause me, I'll give you hints. And then if you get stuck, unpause me one more time and I'll show you the answers. Ready, set, go. All right, you're back. Hopefully you were able to figure out problem 2. There's nothing too crazy about problem 2. As a reminder, we're going to keep the smaller base 2 the same, and we're going to change the larger base 8 into the smaller base. We're going to make it 2. But 8 just doesn't magically become 2. We have to pick an exponent. 2 to the first isn't 8. 2 squared is 4. What's 2 to the third? 2 times 2 is 4 times 2 is 8. Oh, that's good. 2 to the third is 8. We're done. The bases are the same. Now, you may have gotten stuck on 3 through 6, and that's totally okay. They are tricky. So there are a couple hints we need. First hint, on this problem, on problem 3, we're going to change everything into a 2. Because I notice on this side there's already a 2. In fact, there's a 2 to the first power. And the trick that's going to break this wide open is to remember what we did last class. Last class, we saw if we had 4 to a negative exponent, we could rewrite that as 4 to a positive exponent. And so it should make sense that if we have something like 1 over 3 to the 7th power, we could rewrite this by working backwards as 3 to the negative 7th power. They're the same thing, right? We normally moved this to the denominator, but we could move it the other way around. Keep that in mind with the 2 to the first about a way you could move it so it would match this base. Problem 4 is going to be very similar. Problem 4, I'm actually going to go ahead and rewrite part of the base on the right side. Instead of 49, I'm going to do 7 squared. And then keep in mind the same hint that I gave you on 3. Problem 5, my hint is this. I'm going to start with the 2/3 over here to the 0.5x. The base I want to match is 2/3. And I'm just going to start with the numerator first. I'm going to say, well, 4, that's pretty darn close to 2. I could do it as 2 to the second power. And then 9 is pretty darn similar to 3 because it's 3 to the second power. There's one more step you'll need here to finish it off. Okay. Last one, my hint here, 10 to the negative x minus 1, is that we're going to change 0.1 to be like 10, except we're not going to say 0.1. You might remember all the way back to 3rd or 4th grade, you learned the correct way to say decimal. So say 0.1 because it's a little faster. But this is actually 1/10. That's the 1. Yeah, 0.1 is the same as 1/10. If it was 0.01, that's 1/100th. 0.001 is 1/1000th, and so on and so forth. Don't forget, though, this is actually 10 to the first power. All right, see if that helps you at all on rewriting any of these. Don't forget this hint with negative exponents. You'll need them. And once you're ready, unpause, and we'll come back together. Ready, set, go. All right, hopefully you saw some more success, but I'll do my best at an explanation. This is 2 to the x plus 1. I am going to do the same transformation over here. If you have a number in the bottom of a fraction with a positive exponent, you can rewrite it so it has a negative exponent. So this 2 to the first in the bottom of the fraction will actually become 2 to the negative first if you move it to the top. And now the bases are the same. I think problem 4 is going to be very similar. The left side isn't going to change at all, but the right side, we move 7 squared up. This becomes 7 to the negative second. The bases are the same. Problem 5 is a little different. Problem 5 needs us to remember what we learned 2 classes ago with fractions. We learned that if you have a fraction to a power on the outside, you can distribute it to the ones on the inside. And so it should make sense that we can work backwards. If you have a fraction on the inside and you have the same exponent, we should be able to pull the exponent to the outside. 2/3 squared is the same thing as 2 squared over 3 squared. I just undistributed, we'll pretend that's a word, I undistributed the 2. And last but not least, the trick, of course, was with the decimal, and now we know the second trick with our power. We're going to bring that up to become 10 to the negative first. 10 to the negative x minus 1 equals 10 to the negative first. All right, this page was really to show you the process of how we made the bases the same. However, eventually we'd like you to be able to move straight to this step without showing too much work in between. You can always show more work if you need. But in the interest of time and saving paper, I wanted to give you a bunch of space here. And then, when we flip the page, now that the bases are equal, we still haven't solved the problem. You might notice something familiar about these 6 questions. That's right, they are the same exact 6 questions. So now we're not going to show any more work than we did on the first page. In fact, we're going to show less. And then from that, we're going to actually solve the problem. So the first thing we need to do is we need to remember, I'm going to write this as step 1, that the first step is to rewrite each equation so that the bases are equal. And that's on the previous page. Now I'm going to write that step down below, but I'm going to save a bunch of space in case we need to solve. Hint, hint, you'll need to solve, and you'll need that extra space. So 3 to the x equals 9. I am not going to write 3 to the x equals 3 squared in huge letters. I'm going to just do it, saving some space, and just say 3 to the x equals 3 squared. We did that on the previous page. And I'm going to fill in the rest of these. So go ahead and fill them in with me. 2 to the 2x equals 2 to the third. This one becomes, we'll use the space up here, 2 to the x plus 1 equals 2 to the negative first. Just moving straight down, 10 to the negative x minus 1 equals 10 to the negative first. This guy, again, saving some space, we get 2/3 to the 0.5 or 1/2 x equals 2/3 squared. And this guy over here was 7 to the 3x minus 2 equals 7 to the negative second. Notice I'm saving space for the last step because there are only 2 steps to this. Notice that all of the bases now are equal. That is very good. We need the bases equal for this last step to work because our whole point in solving an equation is to make the entire left side equal to the right side. So if we've made the bases equal, the only thing left that's not equal are the exponents. So step 2 is we need to figure out what makes the exponents equal. Here we go. On our first problem, to make the exponents equal, we are literally going to do that. The way we do this in algebra is if we want to make two things equal, we take one of them, the x, the other one, the 2, and then we put an equal sign between them. That's how powerful algebra is. If you put unknowns on one side, unknowns on another, and an equals in between, this will let us solve an equation to find what makes them equal. To solve, the x is by itself, and lo and behold, the x is already by itself. In this case, the answer is 2. And again, you should probably be saying, duh, 3 to the second is 9. We're there. But it gets a little trickier. 2 to the 2x equals 8, so let's try this process again. We want to see what x will make 2x, the exponent on the left, and 3 equal. And now we do need to isolate x, and we do that by realizing 2 is multiplying, so we divide. And this gives us x equals 3 over 2. Remember, we can leave this as a fraction. Of course, it's also a decimal if you prefer 1.5. Third problem. You might have seen something like this and think, I have no clue what x is going to be. But now that we know our superstar shortcut, we know we have to take x plus 1 and negative 1, the exponents, and set them equal. And then ask ourselves, is x alone? Well, no, there's an adding 1 attached to x, so we're going to subtract 1 from each side, and this gives us x equals negative 2. Easy as that. Set the bases equal, then solve for x. Let's try these last couple. Okay. 3x minus 2 and negative 2, and we solve. Add 2 to each side. 3x equals 0, right? Negative 2 plus 2 is 0. That's why we zeroed it out over here, but we do need to write the 0 on the right side of the equal sign. We finish this off, divide by 3, or you could have even said, oh, I know what this is going to be right now, right? X equals 0. A couple to go. We're going to take that 0.5x equal to 2. And I'm actually going to write 0.5 as 1/2 x equals 2. So that way we remember to undo a fraction, we multiply by the reciprocal. But 2 over 1 is just 2, same thing. So I'm just going to show 2 on that side. Everything cross reduces, and we end up with x equals 4. Last problem. Negative x minus 1 has to be equal to negative 1. We add 1 to each side. Negative x equals 0. Well, hopefully we've learned by now that if negative x equals 0, x just equals 0. Negative 0 is the same as 0. Okay, I did promise you a lot of practice problems for today, and I want to hold to that promise. I actually have 18 fun-filled practice problems. Now, if you're in class, these 18 problems are going to be done with 18 classmates. So what you're going to do is either working with someone else or on your own, you're going to do the first problem. And then once you finish the first problem, you're going to pause and find someone else in the classroom, maybe the person you worked with or someone else who has also finished the first problem. You're going to check your answer with that person. If you agree, you're going to sign each other's paper. And make sure you know the person's name, because your teacher is going to ask you at the end, who's this signature, who's that? You do need to know their name. You're only going to sign their paper, and they're only going to sign yours if they agree with your answer. If the answer looks good, great, you sign. If it doesn't, you'll need to work together to figure out what the right answer is. And then you can either go back to working on your own, go back to working with a partner, find a new partner, and you're going to work the second problem. You need a new signature, and you're moving on. 18 questions means 18 signatures. All right, so you're going to work that. At some point, if you guys do need a hint, I'm going to go through and let you unpause me, and I'm going to show you what each of these are going to look like when the bases are the same. And then if you need a further hint, I will give you the right answer, but not the work to get there. So let's have you guys go ahead and try each of these. Again, if you get stuck, you can always unpause and skip to the one you need, and you can listen to my quick speech for it. So, ready, set, go. All right, you're back. Let's go ahead and give you some hints on each problem. I'm not going to give you the whole thing. That would take way too long to do 18 questions, but I'll at least give you the setup and the answer. So, problem 1, our bases being the same should be 3 to the 3x and 3 to the third. 3 to the third. And your final answer, by the way, should be 1. There is some work you need to show in between. Okay. Problem 2, we should get 2/5 to the 4x, and we should also get 2/5 squared. Your final answer here should be 1/2. Problem 3, we need to get 3/2 to the x minus 3, and also 3/2 squared. Final answer should be 5. Problem 4, we should end up with 4 to the 5x minus 1 equals 4 squared. And our final answer for this guy, you can either get a fraction, 3/5, or you can get the decimal, 0.6. Problem 5, 3/4 to the 3/2 x. That won't change, but this crazy other fraction will. This will just be 3/4 to the third. Remember, pretty much everything today is going to be a cube or a square, couple exceptions, because that way you can use your perfect squares and perfect cubes chart. Final answer should be x equals 2. This next one is legitimately a little tricky. We have a negative on one side, and that's not going to change. But on the other side, you have a positive. How do we make a positive into a negative? Let's just go for it. Let's just say it's negative 4/7. Ignore the negative for now. 4 and 7 squared, each get the fraction there. But how come we can turn a positive into a negative? Well, imagine you actually tried negative 4/7 times negative 4/7. A negative times a negative is a positive. Same thing down here. So there are some cases where you're like, whoa, how do we turn a negative to a positive? That's because a square or any even power will always turn a negative into a positive. The answer here, by the way, ends up being negative 1/2. All right, on to this back page. Okay, nothing too terrible yet. However, this first one can be a little tricky. The left side, I should zoom in again, sorry. The left side won't change, and this is why it's tricky. We didn't actually change the larger number. I'm going to change the smaller one. 1 is such a special number with exponents. You can change any number into 1 as long as you have a 0th power. So let's make the bases match. 17. 17 to the 0th is 1. And our answer here, by the way, is 5/2, or if you want the decimal, 2.5. 3/8 to the 5 minus x, and this is going to be 3/8 cubed. Our answer will be 2. 9, another one of those negatives, but notice on this time they're both still negative. So I am going to group the negative in with the fraction, and then we can say this is cubed. If you do a negative times another negative, your answer is still negative, and your final answer here should be 2. All right. Nothing too bad so far. 1/3 x plus 2 equals 7 squared. Final answer, you actually get 0 here. That doesn't mean no solution. It just means 0. Makes the left side equal the right. This next one's tricky, and I'll show you a couple steps. So 6/7 to the x. I'm going to start by just rewriting 49 as 7 squared and 36 as 6 squared. You might notice an issue here. The 7's on the top, the 6 is on the bottom. We want those swapped. So let's swap those. We can swap them. We can move the 6 up top, the 7 in the bottom. But as you move them, what happens to the exponents? They change sign. And so we end up with, whoops, that was a parentheses and a 6 at the same time. 6/7 to the x equals 6/7 to the negative second power. And our answer here, I bet you can see, is just negative 2. All right. 12 was a silly one. You'll notice that the negative's on the outside of the parentheses. So the very first thing I did is I went through and I actually multiplied both sides by -1. That just gave us positive 5/6 to the negative x equals positive 25/36. Once you're here, then to make the bases the same, it isn't too bad. You end up getting 5/6 squared. The final answer, by the way, is -2. Just a couple to go. Now, 13 and 14 I thought are really good problems. We're going to do more of these next class, but these ones are going to have us change both bases. And the reason I know to do that is because I can't change 8 into 4. 4 to what power gets us 8? I'm not sure. 4 squared is 16, not 8. However, both of these can be changed into 2's. So here's what's not going to change, and here's what is going to change. 4 is 2 squared. 8 is 2 cubed. And in fact, I'm going to go one step further. I'm going to remember one rule with exponents. When you have one on the inside of a parenthesis and one on the outside, you multiply them. So this is 2 to the 6x equals 2 cubed. And then you can solve. You should end up getting 1/2. Here's another double change. We have those 8 and those 4's again, so that should be a pretty good giveaway. Okay, 4 minus x is not going to change. 4 and 49, I think 2/7 squared. 8 and 343, I think we can do as 2 over 7. 343 I recognize as 7, both cubed. And then, same thing before, I'm going to go ahead and multiply these two exponents together. How do I multiply 3 times everything? Well, I distribute. And so this gives us 2/7 to the 12 minus 3x equals 2/7 squared. Final answer when you solve is the fun fraction 10/3. I would suggest you don't write this as a decimal. If you do, you'll get 3.333 repeating. That's pretty gross. Fraction's much nicer. All right, back into the less terrible ones, I promise. 15, here's another one of those ones. So I'm going to keep the 1,237,650 to the x. And I'm going to change the 1 into 1,237,650 to the what power will make it 1? Oh yeah, the 0th. And by the way, your answer here should be 0. You can probably see that right away. 3 to go. All right, this guy also breaks away from our table a little bit. I'm not going to change the 10. I'm back to changing the larger number. It's going to be 10 to some power. What power? Well, 10 to the first is 10. You square it, it adds a 0. Cube it, it adds another 0. Right? To the 4th power makes 1 with 4 zeros. We could have seen the 4 zeros here and realized that's a 4. Final answer, by the way, will be 40. 17. What I did here is I went ahead and said, well, this is 1 over 2 to the 1st power, and this is 1 over 2 to the 2nd power. That way we can see they're both powers of 2. I almost forgot my exponent. Then we can bring both of those up. So we end up with 2 to the negative 1st and 2 to the negative 2nd. 4 minus 2x didn't change. And then distribute your negatives so that we have a single base and a single exponent kind of. Negative 4 plus 2x equals 2 to the negative 2nd. Then solve. When you solve, you should end up with an x of 1. Last problem. A few things to check out. This 1 over 2 to the x, we might realize that we're actually able to do a few things with this. I'm just going to bring the 2 to the x up. That brings it to 2 to the negative x. And then how do we match 8 to that base? Well, that's 2 to the 3rd. Final answer here will be negative 3. So get that practice in. Make sure you're comfortable with these. Next class, we're doing more of the same. What's really the only difference? Well, next class, you might have more of those change both bases. But in particular, we're going to see exponentials that now have x on one base and on the other. So maybe the problems are a little bit harder. We're going to see a little bit more of where we had to distribute on the inside. And that's really that. So thank you for getting your practice in. I'm excited you tuned in to learn about solving exponential equations algebraically, and I will see you back next class.